Good morning, everybody, and welcome to this 10th edition of the Code of the Month presented by CASTIEL 2. Today we have the pleasure to have Herbert Owen as speaker from Barcelona SuperComputing Centre and the CoE EoCoE. He will present the code Alya. It's a multiphysics code, a very major multiphysics code, which he will present mostly the use cases developed in EoCoE on wind turbines and wind plants, but also some applications in automotive in the aerospace area. So I'm really happy to have Herbert here, and now the floor is yours, Herbert. So one thing, if you have questions, we would have a Q&A session at the end. You can also type your questions in the question box or just in the chat. So we'll do that after the talk. So now, Herbert, the floor is really yours.
Thank you very much, Gautam. So, I'm Herbert Owen. I have been working in Barcelona SuperComputing Centre for 15 years now, and I will present you Alya, that is a mature code, and also a new code that is called SOD2D. In this case, it's high-order code that we are developing that runs fully on GPUs. So Alya, said before, is a mature code. It's an HPC finite element multiphysics code developed at Barcelona SuperComputing Centre, and it has a wide range of applications. I would say the most important applications is fluid dynamics, but also it can couple this with temperature coupling, tracking of particles. For example, you see there the simulation of a nose, and it can also solve solid mechanics problems. So, it's a relatively complete multiphysics package, and it uses linear finite elements. The code is one of the 2 CFD codes in the praised benchmark suite, so its scalability has been tested on most European supercomputers. And here you can see several applications on different fields, from a wing to the respiratory system, combustion cases, and more academic cases such as the flow behind that figure. So the code participates in several centers of excellence. Here I am in representation of EcoFree. That is a project I have been participating now for like 8 years, from ECO1, ECO2, and now starting EcoFree. But the code also participates in Accelerat, SIG, where the application is more in aerodynamics. I will show some examples, and we have also participated in RACE related to artificial intelligence and CoEs in combustion. So first I will talk about some of the benchmark cases that we have been doing on wind energy and the kind of applications that we do. This is the Hornamosen benchmark. This is a case where we want to simulate the flow over a piece of land. This is in Sweden, where there are interesting experimental measurements that we want to reproduce to test the code and compare it with other codes. Yeah, and then here I show some of the results that we obtained for this case. This is an LES simulation, and on the bottom you can see the terrain. Actually, there is also a lake, the flat part that you see on the right. And here we can see the complex flow structures that are formed in these two cut planes. Some other benchmarks that we have also participated, one of them is the ALAIS benchmark. This is in Spain. It's a very complex terrain. There is a valley between two mountain areas. Yeah, and here we can see some of the comparisons that have been done within this benchmark between Alya and several other codes, including WRF, the LES version of WRF, also Ellipsis, the code developed at DTU. And well, we can see that there is still some difference between the different codes. These cases are very difficult to actually take into account all of the physics, and this is why you see some spread between the different codes. Boundary conditions are very difficult. How you couple with the forcing from the mesoscale is also very different, very difficult, and there are different options. So this is why you see some differences between the different codes. Alya has provided very nice results, and one of the things to point out is that Alya has been run both in runs, simulation, and steady runs, and LES. It's the only code here in the comparison that has run in both mode. Ellipsis is only runs, and WRF has LES. Yeah, and so this is something that we are pushing. I don't know if you know the difference between runs or LES. LES, you try to simulate the big scales. In runs, you just model them. So when you have an important flow separation, LES is more accurate, but also more expensive. Well, this is why it makes a lot of sense in a center of excellence where we are pushing for exascale. Some other cases that we have also participated, breedingness, also again in Sweden, and this is a case with a lot of forests. Yeah, and well, here we can see a cat over at 40 meters above the ground, and we can see the velocities obtained with different codes. Ellipsis again, Alya, two different versions of OpenFOAM, and also the PAN code. Yeah, well, again, Alya provided good results for this case, and there is a paper, if you're interested, where you could see more results. So what is Alya doing? It's simulating what is called microscale simulations. Then you have the mesoscales, that are the kind of simulations that are used for weather predictions. Those are over much bigger pieces of land, much bigger domains, and obviously with a much coarser resolution. So we focus on trying to be able to model correctly what happens when one has this complex terrain, or being able to correctly simulate the waves behind the wind turbines. Regarding benchmarking, I have to say that we are a bit sad at this moment, because perhaps the most important benchmark at the moment is the Awaken benchmark. This is being organized in the US. But contrary to the previous benchmarks, this is a paid benchmark, and the different countries have to decide if they pay or not for participating, and it seems Spain will not pay, so well, we are a bit unhappy that we won't be able to participate in this method. Some other things that we have been doing in the wind area, the previous simulations are simulations all over a wind farm, and one can also be more interested in simulating the wind turbine in more detail. And there are different ways of simulating the wind turbine. Later I will show some other options to simulate the wind turbine, but this is what is called a full rotor simulation. That is the most accurate way of simulating a wind turbine. You actually take into account the wind turbine blades, and you are resolving the real wind turbine blades. These wind turbine blades are obviously rotating, as you can see here. So you have a part of the mesh that is rotating together with the wind turbines, yeah, and the rest of the mesh is fixed, and you have a coupling between these two parts of the domain. Yeah, well, this is a simulation that was actually quite difficult, and we are quite happy that we could produce this simulation in Ecuador. Now I will step over to the second code. This is called SOD2D, but it is a totally free 3D code. It doesn't have 2D capabilities. It started in the PhD thesis a couple of years ago, and initially it was 2D, but now it's just fully 3D. So, well, this code also participates in EoCoE, Accelerate, and SIG, and perhaps the main differences with Alya is that it is a high-order code, and then it does not have any intention of being a multi-physics code. It is centered just on computational fluid dynamics, compressible and incompressible, and also the thermal coupling. This is the physics that we are interested in having in this code. It is developed at the large-scale CFD group at BSc, and is the code that we are currently using most. Moreover, it's a totally open source code. Alya, you can get access, but it's not open source. You have to sign some agreement, and you cannot use it for commercial purposes. Instead, SOD is totally open source, and moreover, it has been developed from scratch to work on GPUs, and it works fully on GPUs, something that in Alya is work in progress. So some of the simulations that we have been doing with this code, automotive and also aircraft aerodynamics, we have a very nice collaboration with Airbus, and we are part of these other projects that I mentioned before, Accelerate and SIG. Here we can see the flow over the CRM model. This is a very important benchmarking exercise that is called the High Lift Prediction Workshop, where we have been simulating this aircraft, and you can see the complexity of the flow for this aircraft. And well, as I said before, the code is fully GPU. It has been programmed in Fortran, and for the GPU implementation, we use OpenACC, and we are very happy with the performance. The code has been tested in several European supercomputers. In Mare Nostrum 5, that is the supercomputer at BSc, we have tested up to 2,000 H100 GPUs. This is nearly half of the machine, and we expect to test it on the full Mare Nostrum 5 as soon as we get access. Despite the code is relatively new code, we have tested it against NEC 5000, that is a very well-established high-order spectral element code, very similar formulation to what we have in SOD, and it performs very well. The computational times are very similar, and for the accuracy in some of the cases of LES simulations, it's perhaps a little bit more accurate than NEC 5000. These comparisons have been done by the NEC 5000 group, so this is something that we are very happy because it's not subjective. Now we will talk about the collaboration with the industry that I understand is something that is of great importance here as a code of the month, to see if we could establish some other collaboration with the industry. We can help the European industry to move forward and get advantage. So we have been working with different companies, both big and small, perhaps in the wind energy sector. For clearly the most important company that we have been collaborating is Iberdrola. Iberdrola is a global, worldwide leader. It is present all around Europe, the United States, Brazil, Africa, Australia, Japan. So it's a very big company. And we have been working with them on wind resource assessment. So these simulations over the complex terrain where they are planning to build a wind farm, to better know the energy production that it can provide, and also where to better place the wind turbines. So this is a collaboration that is now that has been ongoing for more than 10 years now. We had to introduce several new physics into the code and also numerics to address the needs of the wind farms. We had to introduce Coriolis forces that are important when you simulate a wind turbine. canopy terms for the forest, actuator these models to take into account the wind turbines, thermal coupling when we want to deal with stable and convective regimes, and also simulate a diurnal day cycle. Modifications for the Runge turbulence models that are specific to winds, and modifications to boundary conditions. So there have been several modifications that we have been doing to Alya, and we are also starting to do now in SOD2D. Moreover, in order so that Iberdrola could actually use Alya themselves without our interventions, they have been a user of Alya. We developed specific pre and post processing tools so that they could use Alya as an alternative to the commercial codes that they have been using for quite a time. So regarding the pre-processing, we developed a mesh generation that is specifically suited for the wind farms. So you have a central region where you need a relatively fine mesh, that is your region of interest. And then you have a bigger domain where you go to flat terrain, you artificially go to a flat terrain so that the boundary conditions can be introduced correctly. Yeah, here we are seeing this plotted over Google Earth. So this is a way that they found very comfortable to be able to look at the mesh that they had generated, and also to check if the roughness, the canopy, and the height of the terrain had been introduced correctly. Yeah, in these cases, the meshes that we use for wind energy are hexaedral meshes, but Alya can deal with different kind of elements, tetraedra, prisms, pyramids, and obviously hybrid meshes. So in the mesh generation process, we start with a topography that can be given as an STL, a contour map, or a set of points, whatever is more comfortable to Iberdrola or what they typically use with the commercial tools. We then filter noise that can be in this data. We generate a quadrilateral surface mesh. We do some optimizations to this mesh, and then we extrude in the vertical direction to get the hexaedral volume mesh. Here we can see some details of the mesh and initial mesh, and also in the right, the optimized mesh that, well, especially when you have a very steep slopes in the terrain, the mesh gets quite distorted, and so we have tools to optimize the mesh so that we can obtain good results. Moreover, we can also include the wind turbines using actuator discs. So this is like a force in the area where the wind turbine is located. Yeah. And for this, what we use in Alya is we generate a specific mesh, not only in the disc, but also behind the wind turbine, where you typically you have a wind turbine wake that is smaller velocities and higher turbulence. And well, this is something that we have prepared for them, and we have used it to simulate very big wind farms. Here, I believe it's around 100 wind turbines. Some of the results that we have obtained with these meshes, so you can see the different wind turbine wakes and how they interact between each other, and also the energy that can be produced by the wind farm that is in final the data that Iberdrola is most interested in. And finally, we have developed post-processing tools so that we output all the information that Alya provides, that typically is velocities, pressures, tractions on the ground, but we put it in the format that is more comfortable to Iberdrola, to what they are accustomed. We get the wind fields, but also waveful distributions, turbulence energy and annual energy production, and we can plot this over Google Earth so that it is very comfortable for them to see. So this is more or less the workflow. So we have some pre-processing tools with Mesh and AliaFix that generate the mesh and apply boundary conditions. Then we run this in the supercomputer. And finally, we process this and put it into the format that is comfortable for Iberdrola. We have also collaborated with small and medium enterprises. This is quite difficult. I believe this is something that, well, the European Union is always pushing for us to try to make this. And we are very interested in doing it, but we recognize it's difficult. I'm a mechanical engineer, and several of the members in our team are mechanical engineers. And well, I believe that well, it's what we like to do. We want not only to produce impressive simulations, but that they are useful. Here, it was a collaboration with Vortex Blades. This is a small SME that tries to generate energy with a mast that oscillates. It enters in resonance, and in this way it generates energy. We have participated with them first with a shape praise project, and then actually they paid to us for some time from an European project in which they were involved, and we did these very nice LES simulations for them, where not only the flow, but we also have the movement of the mast. Finally, I want to say that now we are also collaborating with OceanWinds. OceanWinds is a joint venture between ENGIE and EDP, so two very big companies that get together to work in offshore wind energy. They created this new company, and we have been working with them. In this case, we are using SOD2D, the new code. That well has the advantage that it is totally open and they can have full access to the code. These are some preliminary simulations with actuator disk and SOD2D. Finally, I want to say that we have also participated with other big companies such as Airbus. We have a strong collaboration at the moment, where the code that they typically use is a Runge code, and we are now using SOD2D to perform the same geometries, but using LES, so it is much more computational intensive, but in cases where you have important flow separation, it can provide much better results. Finally, we have also worked with SEAT, the car company from the Volkswagen Group, where we simulated a car with the rotating wheels. And well, here you can see some of the results. Finally, regarding other small companies, this is a company called Juan Design that is an important player in the world of race for sailing competitions. They have been designers of the Volvo Ocean Race hull, and also they have participated several times in the America's Cup. They are the designer of the boats that are used in the America's Cup. And this is well, a collaboration we had several years ago, actually, when I started in BSc, where we were trying to use our code as an alternative to commercial software. In the right, you can see the kind of simulations that we were doing at the beginning for the hydrodynamics, the shape of the wave that is formed when the hull moves in the water, and the shape of the wave affects strongly the pressures that you have on the boat, and also you have to take into account the equilibrium position that the hull attains. This is why you see this movement of the boat. We also did at some moment some collaboration, and this was also in a shape-based project for the aerodynamics part, where again we were trying to showcase the advantages that can be had by using LES instead of runs, and you can see that you can much better simulate the vortexes behind the scenes. So well, thank you for your attention. Here I leave a final animation of the flow over complex terrain. This is the balloon example, another of the benchmarks that we have run. Thanks.
So thank you very much, Herbert, for this very impressive talk. And the floor is open for questions. So either in the chat or via this special question Q&A tool we have.